Hi everyone, I'm Andrew Hoffman. I'm a software engineer, a security researcher, and a technical author based out of the Pacific Northwest. Today, I'm going to talk to you about what I believe is the most secure programming language. And I'm going to attack this from a couple of different angles. I'm going to use a three-pronged approach that incorporates a lot of data in addition to some insights. And we're going to deep dive and look into a couple of these languages from a very deep perspective that allows us to determine if it is the language itself that causes it to be secure, or if it's the ecosystem around that language. So today, in order to determine what the most secure programming language is, we're going to start by looking at the core language design. We're going to say, what built-in security mechanisms exist in this programming language? Is the language architected in a secure way? Does it use a secure by default pattern? In other words, does it prompt you or force you, the developer using the language, to write your code in a secure manner? Does it provide design patterns that are inherently more secure? So that's going to be the core language design component of this video. Next, we're going to look at the language infrastructure. Does the language have a number of secure libraries for routine tasks? Are they well maintained? Are they maintained by people who know a lot about and value security? We're going to look at things like cryptography libraries, authentication libraries, libraries for interacting with databases. We're also going to look at the community. Are there tutorials and community outreach from the language team itself that emphasize security? And finally, we're going to look at some data and we're going to say, have there been a lot of vulnerabilities in this programming language? And what companies have had major products hacked because they used said programming language? And using those three major categories, the intrinsic language design, the infrastructure around the language, and the data on vulnerabilities and hacks that have occurred in relation to this programming language, we're going to be able to determine, using the facts, reasonably accurately what the most secure programming language is, so that if you're interested in writing secure code, maybe you want to build applications in finance, applications that interact with the blockchain, maybe healthcare data, or you just really care about your customers, you'll be able to choose the programming language that will give you the most security out of the box. So let's get into it. So it's time to dig in deep in order to answer the question, what is the most secure programming language? Now in the intro, I said we're going to start by looking at the core language design. But prior to looking at the core language design, we need to establish what a few of our candidates for the most secure programming language are. In order to do this, we're going to start with the winners from the last video, what is the best programming language to learn in 2022? In this video, I looked at industry trends, I looked at a number of data points and provided some insight, and we came up with the idea that JavaScript, Python, C#, and or C or C++ are probably the best languages to learn for 2022. So we're going to be analyzing those in this video, in addition to two languages that are often noted for their investment into security, Haskell and Golang. These are two newer languages, or at least becoming adopted more recently, that have significant investment from the core teams into making sure the language is secure. So the first question that we're going to ask is about the type system. Every programming language has methods of storing data, and that data is stored in memory, but not every programming language makes you store it the same way using the same shape. So oftentimes programming languages that are designed for developing software quickly make use of what's called a dynamic type system. So dynamically typed languages allow you to store whatever type of data you want in a memory address. Statically typed languages, on the other hand, allow you to store only a very particular type. Now, as you can imagine, statically typed languages typically are a little bit more secure because they prevent common programming errors that occur when you try to assign an object with the shape A to a memory address that previously held an object with the shape B. And the reason that is because a lot of times you'll have a function that expects an object, and in a dynamically typed language, that function might not actually know what type of object it's getting. So it might perform operations on that object without actually looking at the underlying structure. Now, in a statically typed language, functions always know what type of object they're getting. They always know the shape of the object that they're getting. So here, if we look at JavaScript, JavaScript is indeed a dynamically typed language. Python is also a dynamically typed language. C# is static. C and C++ are both static. Haskell and Golang are static. So that's a negative point. So that's a loss of a point for JavaScript and Python in the world of secure by default programming language architecture, and it's a positive point for C#, C, C++, Haskell, and Golang. Now we're going to move on to the next thing, which is memory management. So we're talking about how all programming languages, a core concept in programming is this idea that you can create memory addresses, or you can allocate memory addresses, and you can store data at those memory addresses or use those memory addresses to point to other data. Now, one thing that's not talked about a lot in the computer science world is the fact that manual memory management is actually a downside when it comes to security. See, when you're dealing with memory, you need to be aware that there's other applications on your computer that are also dealing with memory. And a very important thing is to make sure that none of the data ever overlaps, so none of these memory addresses ever overlap, so your application can't read into the memory of another application. And you also just want to be aware that there are ways in which you can store data in memory that are much more secure than others. And when you start looking very deeply at memory management, you learn that generally speaking, leaving memory management to the programming language is much safer than trying to perform all the memory management yourself, because the computer, the programming language itself, is not going to perform routine types of mistakes that a developer could easily perform. So we consider having memory management baked into the language as a positive in the world of security. And when we're talking about memory management, JavaScript does have its own memory management. It has its own garbage collector, etc. So does Python, so does C#. C and C++ do not, but Haskell and Golang do. So by using these automated methods at the compiler level for managing memory, the amount of programming errors that can occur in someone's code that lead to security vulnerabilities is significantly reduced. Finally, what we're going to go on to is we're going to look at different ways of writing your code. So programming language historically have fallen into a couple of patterns that are often called in computer science programming paradigms, sometimes called design patterns. And design patterns are not about how the code functions at the interpreter level, but instead how is the code written. So functional programming is a style of programming in which functions are first-class citizens. So functions can have names, they can also be passed to other functions. And you can build higher order functions that are capable of generating new functions. And also you can make use of what are called pure functions. Now from a security perspective, a pure function is a function that has no side effects. As you can see here, no side effects. So what does that mean? Well, typically if you're looking at an object-oriented language, a traditional language like Java, for example, you're building up models of everything that you're operating on. The downside to building up models is each model has its own state that it needs to manage. And the more state that you manage, the more likelihood there is that state can be leaked to other classes, other functions, where it is not supposed to end up. So object-oriented programming, while it has its uses, is actually not as valuable from a security perspective as functional programming. So in functional programming, everything is a function, and we can pass a lot of data throughout these functions, but we don't build these functions with state management in mind. So typically we're trying to build functions that don't actually have to do a lot of interacting on state information. Ideally, none. So when we look at these languages once again, we find that JavaScript actually is very good at supporting functional programming. In fact, many JavaScript programmers strongly prefer functional programming. Now JavaScript is a flexible language and it is possible to write it in an OOP style. However, even the implementation of OOP in JavaScript is built on top of its prototypal inheritance system, which really leans in the direction of functional programming. Python is also a functional language. It makes it very easy to write functional style code. And unfortunately, C# is one of the strongest OOP languages out there. So C# is going to get a negative point for this, while JavaScript and Python get a positive point. Haskell and Golang, on the other hand, Haskell is definitely a functional programming language. In fact, Haskell has a large number of features that allow it to be functional with the end goal of keeping functions stateless for the purpose of security. So that's a big plus to Haskell here. Golang, on the other hand, is not a functional language. It may be possible to write a little bit of functional code in Golang, but at its core, Golang is not a functional programming language, so it's going to lose a point here. So if we are to summarize the section 1 of the analysis, which one of these languages are most designed with security in mind, we find that language design really falls on Haskell of all the languages we evaluated. So Haskell is not only statically typed, but it has its own built-in memory management and is a functional language. So now we're going to start moving into part 2 of our analysis in order to determine what the most secure programming language is. Part 2 is all about language infrastructure. So in part 1 we talked about the language itself. Now we're going to talk about the tooling around the language, often tooling developed by the community. So one of the best ways I could find in order to analyze the tooling was to say what implementations of bcrypt exist in all of these different languages. So oftentimes one of the most common things that you have to do in a web application is perform authentication. In order to perform authentication, you need users to be able to sign up, and you need to be able to hash their passwords in a way that's totally irreversible and totally secure. So you want to be able to protect against rainbow tables. You want to be able to protect against other types of attacks, even brute force attacks. So bcrypt is able to protect against all these things, and like many other modern hashing functions, over time, the more and more times that you try to request the bcrypt function, the slower and slower it becomes. So it's resistant to brute force, even with very rapid hardware. It's resistant to rainbow table attacks, and it's been around for a while and proven itself as a very strong hashing function in the security industry. As you can see right here, it looks as if the bcrypt cipher might go all the way back to 1999 at some point. Now, bcrypt is built on top of Blowfish, and the Blowfish cipher is a symmetric key block cipher. So actually right here you can see this is 1993, and no effective crypto analysis of this cipher has been found to date. So here you have a password hashing function that's been around for decades, that has not been broken in those decades, that is effective at protecting against common types of attacks, and is widely implemented throughout many industries. So let's look at the implementation in JavaScript. So this is actually the Node.js implementation, because it's most fair to compare server-side implementations, given that these are all server-side languages aside from JavaScript, which is a multi-purpose language. Here we can see that the bcrypt implementation for Node.js has about 6.1k GitHub stars, 425 forks. It's used by an enormous amount of people, and of course has about 70 contributors. It is also very well documented, and you can find implementations of the Node.js version in a lot of places on the web. So JavaScript's going to get a +1 for its implementation of bcrypt. Now bcrypt is also available in Python, and as you can see right here, the Python package has about 787 stars, it has 109 forks, 27 contributors, so there's a lot less people using the Python implementation. Granted, it's still probably being used a lot. The documentation is not as good as the documentation on the Node version, and there's not as much contributors, there's not as many people actually making use of this package, so that's really kind of a downside for Python, but it could just be because a lot more people write code in JavaScript than in Python. Now there's a .NET package as well. Its popularity is a little bit closer to the popularity of the Python implementation. Still has pretty good usage. There's only 13 contributors to this package, and the documentation from what I read was okay, but nowhere near as good as the Node.js documentation for the bcrypt package. Now if we jump over here, this is the only implementation I could find in C. It turns out bcrypt is actually not as popular in C, at least based on my research. So moving on to Haskell, you'll notice that if we go to haskell.haskell.org, we'll see this bcrypt package, and it's very easy to find. However, when we look at the authors, we find that it was uploaded by Andrew Miller in 2017, and it points to this GitHub repository. So this is a package that is an open source repository, and if we dig into it a little bit further, we actually find out that it's just a Haskell binding, and it's a binding to the C library that we looked at a little bit earlier, which was available here. So this isn't an implementation inside of Haskell, but instead it's just a set of bindings that allow you to make use of the C library implementation for the bcrypt hashing library. So that's a little bit of a downside on the Haskell side. However, from what I could read, I actually was able to find that there is a number of very well supported crypto libraries in Haskell outside of just the pure bcrypt implementation. Now if we move on to Golang, the Golang implementation is actually quite interesting. So if we go to Golang over here, we see that there is a set of crypto libraries, and one of those crypto libraries is bcrypt. And inside of this, if we look a little bit deeper, we find out that this library is actually maintained by Google, at least as far as I can tell. So in other words, the implementation of bcrypt in Golang is probably pretty positive. It's probably pretty well maintained, given the fact that it appears as if the bcrypt package is actually developed by the developers of the Golang language and maintained by the developers of the Golang language. So that's actually a big positive, if I'm reading this right, for Golang. So the final metrics that we're going to use when trying to determine what is the most secure programming language is what type of vulnerabilities occur in each of these languages, how frequently do they occur, and what companies have been hacked as a result of choosing a particular programming language. Well, in order to figure this out, we're going to jump over to WhiteSource. And this is a company that actually did a study trying to figure out how programming languages measure up when it comes to security. And the way that in which they did this is they actually went over to GitHub. They looked at the issue trackers, they looked at the National Vulnerability Database, and they tallied up how many vulnerabilities were existing in these sources on a per language basis. So the key insights they note right here is vulnerabilities in C amounted to about 50% of all reported open source security vulnerabilities. Now there's probably a number of reasons for that. As we talked about beforehand, C has been around for a very long time. Also, C is a language that doesn't provide you a lot of guiderails, so you can write it in any way. We even talked about that when we talk about memory management. So they also mentioned that the most common vulnerabilities are cross-site scripting, input validation, permissions, privileges, and access control. So this is a downside for this particular video because a lot of these are actually client-side, or at least have client-side components. Now obviously your input validation should occur both on the client and the server. Permissions is on the back end. Information leaks involve sending data to a client, and cross-site scripting occurs entirely on the client. Finally, they say that the use of automated tools and bug bounty programs have changed the game. That is definitely true, unrelated to this video. But they say we've seen a spike in security vulnerabilities, but the highest severity vulnerabilities have decreased in most languages. So that's a good sign for all the languages involved, that although more security vulnerabilities are being reported, each security vulnerability being reported is generally less severe. So let's look at the list. So the most security vulnerabilities were found in the C programming language, and as we've talked throughout this video, the C programming language is generally not a good language for writing secure software. It does not provide secure guidelines. It does not provide secure by default architecture. It's a flexible, old language that provides you a lot of low-level power, which can be dangerous when we're talking about security. Now PHP we've talked about in prior videos. Now PHP architecturally has a number of issues alongside Java that make it difficult to write secure code. Now as we can see, JavaScript is right below that. Unsurprisingly, there are certain types of vulnerabilities that only appear in web browsers. A lot of people are using web browsers. So this doesn't necessarily tell us if the world of JavaScript is actually less secure, or if the JavaScript of the client is less secure. Python falls after JavaScript, followed by C++ and Ruby. Well, really what we can actually gather from this is that Python probably is a little bit more secure than Ruby, a little bit more secure than JavaScript, but we already knew that. Now, if you look at the trends over time, you'll see that actually C vulnerabilities are increasing. So it's not just the fact that it's an old language, it's also the fact that it's just a very powerful language with no guide rails. Now, if we look at C++, you'll see that C++ vulnerabilities are relatively the same. Typically, we bump these two into the same category because C++ is a superset of C, so they share a lot of the same common issues. We pulled Java off this list because, as we spoke about prior, C# offers some better functionality and tooling than Java in today's world. And this leaves us with JavaScript and Python. If we look at JavaScript, we can see that the amount of JavaScript vulnerabilities peaked in 2017, seems to be on a downwards trend. And likewise, if we look at Python, it seems like Python probably peaked actually in the 2013-2015 range, but is decreasing potentially because of the adoption of Python 3 versus the older versions of Python, which were very popular for a long amount of time. So what can we gather from this? Well, one thing that we can say is it doesn't seem like there's a ton of information already out there in regards to languages like Haskell or Golang. But what we know is that dynamically typed languages and languages that require manual memory management typically have a disadvantage when it comes to security. So when we're talking about this data, one thing we can say is it's probably still a downside for JavaScript and a downside for Python. Maybe less of a downside for Python potentially, but then again, we don't actually know what the sample size for JavaScript versus Python was. So this data feeds back into our original topic, which was core language design. And from a core language design perspective, it's very obvious that Haskell, of all the languages involved, has the best core language design from a security perspective.